So far, we've focused on designing clean programs with classes and objects. Today, we're shifting to learn how we can actually organize lots of objects inside those programs. That's where data structures come in. A data structure is simply a way to store and organize lots of objects so it's efficient to use and look for things and add things and remove things. Python gives us so many built-ins data structures plus many separate libraries such as Numpy, Numpy arrays, just for working with numbers and fast calculations and holding different type of objects. And each one shines in different situations. Um, I'll walk through the commonly used ones, um, when to use them, talk about some examples. Some of them you already know probably. Okay, starting with the first one. As soon as you learn Python, probably one of the first things that you learn is how to work with the list of numbers. This list is one of those data structures. It's basically a concept, and we can actually use this data structures to have access to this concept of list. Basically, we can hold on to all objects or numbers in order. Once we add objects, we can go back and change the elements, and we are allowed to have duplicate values inside a list. That's basically how you can create a list using brackets. We can add more elements at the end of this list by using append. I'm using numbers, but this could be any type of object. Could be like customer object, could be car object, could be anything. Could be strings, could be float values, could be anything. We can change the elements by knowing the index of those elements. So for example, we are changing the elements at the index of 1. All the elements start from um, the in list and other sequences in Python. The first item always start with the index of 0. So when we say, okay, let's change the element at the index of 1, we are referring to the second element inside the list. So we're updating that. We can do that. We can update elements. Um, and as you can see, I'm printing all the elements. I am printing only like the first element, and we can iterate through list easily by just using a enhanced loop like this, or a normal loop. Lists are created for iteration and looking for things and all these stuff. So this is something that probably most of you are already familiar with. The second one is what we call a tuple. Tuple is a list, okay? It's exactly a list, but the only difference is that once you make one, elements are unchangeable, are immutable. That means once you make one, you cannot go back and change one element. So in case you have a list and you know you're not going to go back and change the elements, using tuple has some advantages because it was designed to be more efficient and faster actually. So this is how you do it. We use parentheses to define tuples. Um, you can just print all the elements by just mentioning the tuple object. You can grab one element by just mentioning the index of that object. You try to change one of the elements similar to what we did in with the list, you're going to end up with um, runtime error. And you can still loop through all the elements, and that's what I'm doing. I'm grabbing all the elements and I'm creating a list out of it. Let me just run this so you can at the same time see all the outputs. Um, all right, so let me just drag this up. All right, where were we? Hmm. All right, we're close set. There we go, tuples. So you print a tuple like that. It says it shows all the elements, grabbing the first element, which is 10, and iterating through everything, converting everything into a list and returning it. That's why you see a list here, because I'm using brackets here. So basically, I'm grabbing all the elements and I'm creating a list out of it. Just something that I just wanted to show you. You can do that. So tuples are exactly like similar to the list, but elements are immutable. That means they are unchangeable. And if you're sure that you're not going to change the element, go with the tuple ones because they're designed to be a little more efficient and faster than lists. Since we are not, since the size is not changing, especially for big data and a lot of objects. The next one is a set. Kind of same as a list and tuple. The only difference is that elements are not being saved inside the set with the same order that you're adding them. So each element could sit somewhere different inside the set. An element has to be unique, so it removes all the duplicates automatically. You cannot have duplicates inside the set. Um, so another kind of big advantage of set is that it allows you to add, remove, and find elements inside it super fast. How does it do that? Um, we're not talking about the details how each one of these data structures work in this course, but it basically behind the scene it generates a hash code for each element, and that hash code generates a specific index. So when you provide the value, it just generates the same hash code, so it knows where inside the list this value is already saved. It doesn't have to go through all the elements to find what you're looking for. It generates hash codes, and based on those hash codes, it knows exactly where each element is going to be inside the list. So it's just going to go grab it, find it, remove it, and everything. So it's very fast, but again, it removes the duplicates automatically. You cannot have duplicate values. Look at that. So I I created a new set, and you're using curly brace for sets. So I added duplicate values, but when I print that, the duplicate value is gone. We only have one of them, which is great. Um, you want to add something, you just add it. You just call the add method. It just adds it somewhere inside the set you don't know. Unlike a list or top, unlike the list is not going to be added at the beginning or at the end. You cannot do that. You don't know where it goes. You just add it and it's just going to put it somewhere inside the set. Um, and you want to check to see if the value is in the set. That's one way of doing it, and it do it super fast. Unlike the list that it has to go through all the elements to check all the elements to look to see if the element that you're looking for is there. That's not the case with the set. It can actually find what you're looking for in a constant time, which is extremely fast compared to list or tuple. So that's the big advantage the set has over um, list and tuple. And there are specific things that you can do. The set has its own operations, like you can combine and union all the elements of two sets using the vertical line. So you do that, you're going to end up with this set 1, 2, 3, 4. Your union, you're basically using the union to kind of append all the elements from both sets. You can get the only intersection elements, the ones that are common in both sets, like that. It gives you 3. Or you can say, you know what, just give me the elements that we have inside this set, but not inside the other one. So for example, if you do this, only gives you 1 and 2 that you have inside A, and you don't have inside B. So 1 and 2 is going to be the answer. There are different operators and methods specifically designed for the set, because in mathematics we want to be able to do specific operations on a set. So Python has all of them. Um, the next one, which is kind of similar to a set, it uses hashing and everything behind the scene, which means adding, finding, and removing is very fast. The only difference here is that the dictionary holds a pair of values, a key and a value connected to that key. Um, so there are so many cases you want to hold a pair of values and you want to refer to that value by just knowing the key. So for example, you want to be able to grab all the information about like a person object, like the address, the name, the height, the weight, by just knowing the social security of that person. So social security here is just a key, and everything else, all the information about that person or that person object now is going to be value connected to that key. Which is good. Like in the list and tuple, we can only have access to the elements through the index, but with the dictionary, we can have access to the element through the different keys, one or more than one different keys. So for example, I'm connecting this key with this number. So every time I say ID, boom, it gives me this number as a value representing that key. Same thing with the name. This is key, this is value, this is key, this is value. And that's how we create a dictionary. You want to, for example, you want to say, um, you can print all the elements of the dictionary, like all the key and values. There we go. And you can use different combinations. You can have like a key as a number, as a string, and the value as a number, or both of them as a string. You can use different combinations. How do you get a value of a specific key? Use brackets. Unlike list that we use index here, in dictionary right there you use like the key and boom, very fast using hashing. It's just it knows where it needs to go and find it. If this key and value is already inside the dictionary, it kind of knows where it's at, and it's just going to go grab it for us. So what we are doing here, we are updating the value for this key. If it does not exist, it's going to add that key value to the dictionary. So as you can see, we didn't have GPA, key, and the value. So once we do that, it's going to add that. And when we're printing it, there we go. At the end, when we're printing it, basically we go through all the elements and we're grabbing everything, all the key values as a tuple. That's a tuple, right? That's a tuple. So basically we're getting all the key values as a tuple, and then we're creating a list out of it. And look at that, now GPA is there. So if the key that you're using is not there, it's going to just add it right there. You want to get a value from the specific key. That's how you do it. Same as like arrays and tuple. You just, instead of index, you just use the key and it gives you the value for that name is Alice in this case. Um, there are also two different abstraction or concepts that we can implement using different things, the stack and the queue. These are kind of tricky concepts because they are not exactly data structures, they are concepts, but we use like list and other libraries to just implement them. So they are considered also data structure, in different programming languages. So what is a stack? The last element that comes in is going to be the first element that goes out. So that's what we call the stack, like a stack of plates that you just put on top of each other. The last one that you put on the top is going to be the first one that you're going to pick. And the queue, like a line that you make like in front of, I don't know, like when you want to get a ticket or something. So the first person that goes in is going to be the first person that goes out. So you add something at the beginning, that element going to be the first element, actually, that we can actually take out of the line or out of the queue. So here I am using just a normal list to implement a stack. Why am I using a list? Because for a stack, I can add something at the end by calling the append function, and it's pretty quick. And when I use pop method, I can remove something from the list super quick. That's why using a list for implementing the stack concept is pretty good. The stack can be implemented with other data structures, but list allows us to add and remove from the stack pretty quickly, which that should be enough for us. So, like I said, we use append to add something at the end of the list, and we use pop to remove something. And this pop removes something from the end of the list. Uh, and once you do that, once you add only at the beginning, only at the end, and remove only from the end, now you are basically mimicking the concept of the stack. So now this is going to be a stack. All right, let's see how the output looks like. So I just added task 1 and task 2 by using append, and when you say pop, here is the task 2 is going to be popped first, and now we only have task 1 inside this tag. So task 2 was the last element was added here. When we pop it out, it's going to be the first element that we're removing from the stack. So that's basically the concept of stack. Again, all these data structures can be used in different scenarios. I'm just going over them super quick so you know what are the commonly used data structures in Python. The next one is a queue. First element that goes in is going to be the first element that goes out. And we can still use list, but list is not going to be efficient because when you add something at the beginning of the list is not going to be fast. Adding something at the end is going to be fast, but not at the beginning. That's why we use the list for the stack, but not for uh, the queue. For us to be able to add something at the beginning of the list super quick, there's another data structure that we need to use, which is called dequeue. Dequeue is another form of queue that you can add and remove elements from both sides, either from the beginning or end. It doesn't matter, and it was designed to give us the ability to add and remove from both sides efficiently. So we're just going to use dequeue to implement the queue, because when you say append, it adds something at the beginning, um, and then when you do pop left, it removes from the beginning, and it does both of them very efficiently. So you can imagine something like this. Like let's look at the output. So we add job one, it's going to be there. We add job 2, it's going to go behind job 1. But when you say pop left, um, it's going to remove the first one that was joined to the queue first, which was job 1. So it's going to give us this one, which was first input. Now it's going to be first output. And this is what we have left is still inside the dequeue. So dequeue is good for adding and removing to the list from both sides. So for that reason and that reason only, we're going to use dequeue inside of for implementing queue instead of a list, because like I said, adding something at the beginning of the list is not that efficient. Adding something to the end is is perfect. Is a lot faster and more efficient than the other case. And then some complex data structures like tree. Um, a tree is going to be used for hierarchical structures. We use node objects um, for holding a tree. These tree data structure is very actually complex and actually very efficient for many applications. But usually students have a hard time understanding the code and everything. You can actually implement fast search and sorting techniques using tree data structure. But again, these are not the topics that we want to learn in this course. So I just want to show you how you can actually create a node class and node objects and basically mimic a tree like this. So you can have a root, and then each root can have left child, right child. You can have two child. If each node has only two child, we call it binary tree. But this is like a general tree, so that means each node can have unlimited number of children. It doesn't matter. This is just an example. I'm basically adding two children or one to each node. There are different concepts about trees, like we have full trees, different concepts. There are so many different type of trees in programming that we can use. I'm just showing you like a very general type. So let's just start with the node one. So this node one is supposed to be an object that we can use as a node or any of the child nodes inside the tree. So this is going to be a constructor. We get a value. We're going to initialize the value attribute here. And then we have this children. This is a list of uh, children nodes that we can actually add here. So the first node that we add here is going to be the left child. The second node that we add at the end of this list is going to be the right child. How do we add a new node as a children to this node? We just call this method. So we implemented this method. It gets a new node, and then using the append, it adds something at the end of this list. That's it. Very simple. Um, Look at that. I created a node. I called it root. That's going to be my root. And then I created two different nodes, A and B. How do I make A and B a child of root? That's it. I just call the add child from the root object, and I just add A first and B next. So which means A is going to be the left child, B is going to be the right child. Same thing with other ones. So I want to add the left child to A. I just call the add child and I just create a new node and pass it along. So C is going to be the left child of A, D is going to be the right child, and I just do the same thing for the B. I just add a child to the B. So this one is going to be the left child. Well, initially it's going to be right when you have one. As soon as you add one more, the E becomes left child, and then the new one becomes right child. Um, yeah, so I guess one example that I can show you that so you can get the idea why students are struggling with the concept of tree is this, for example, this method. Like, how do I print the elements now? The only way you can do that is just by going through all the nodes one by one. There are different ways you can go through all the nodes inside your tree. Like we have um, different techniques and everything. So this one, I just go through them, start from the root, and I just go through all the nodes from left to the right. So I start from, um, let's look at I start from printing the root, and then I uh, grab the children of the root, and I just go through it. And I just go through that, and then I just recursively call the same method for grabbing the details of the next chart, and I just repeat the same thing. So I can use a normal loop and loop through all the elements, but usually we use recursion for going through all the elements of the a tree, which is one of the reasons the students usually have a hard time working and understanding the concept of the tree. But once you understand it, is actually one of the powerful data structures that allows us to do a lot of different things like sorting and searching and adding and removing and finding things in a very efficient time. Um, so these are basically like very commonly used data structures. And then Python has like different libraries for working with numbers, number arrays, and everything, which are absolutely great. Like they're very efficient and fast. NumPy array is one of them. You kind of need to install it if you don't have it. So if you import NumPy and you end up with errors, that means you need to um, just look it up, find it, install it first. Um, so basically, the way it works perfectly for vectorized numeric arrays. Like basically, you want to implement an operation on all elements of a list or something. It was designed to do all those calculations super fast. So all the elements must have the same type. It uses like a specific contagious part of the memory, so it just dedicates a block of memory for it, which is one reason that makes it fast. And it's pretty good with fast math because now you can actually calculate um, or implement a calculation in all elements pretty fast. So if it's not installed when you have this line, so you need to go and look for it and just install it. It's a very popular data structure for AI, machine learning, and basically um, these type of calculations. Why? Because it's efficient. It can hold uh, vectors, which are pretty much what we do in AI and machine learning. So look how I'm using it. I'm defining an alias for it. So I'm importing it, the NumPy, and I'm defining an alias for it. I'm saying, okay, from this point forward, I'm just going to use NP for as an alias for NumPy. And then I create a new array with these elements. And let's look at the output. I can print a type. I can print all the elements. And look what happens when I want to add all the elements by 10. In a normal list, you have to write a loop, grab all the elements one by one, and then multiply it by 10 and save it back inside that. But the NumPy was designed for vectorized numeric calculation, like a matrix. You just say times 10 and very efficiently it's going to go through all the elements and multiply all the elements by 10 for you. You don't need to do it manually, which is the beauty of this library NumPy. Or you want to say, you know what, I just want to add all the elements by themselves. So there we go. It just do it for you. And then you want to grab some part of it. You can use slicing. Um, um, Both for the NumPy and normal list. This is also something you can do with the normal list. So I generate 0 to 9 as a list, um, which is going to be this. And I want to say I'm going to grab some part of this element, starting from index of 2 all the way to index of 7. Index of 7 is not going to be included. So index of 2 is going to be 0, 1, 2. Starting from this value, we stop at index of 7, which is this guy. So the last element is going to be 6. The element at the index of 7 is not going to be included. Or you can say, you know what, with the normal list, change all the elements from index of 2 to 5 to 99. So that means element at the index of 2, 3, and 4 are going to change to 99. There we go, 1, 2, 3. So the second index that we are using is not going to be included um, in calculations. Um, yeah, so these are basically very commonly used data structures. NumPy is a very important one. So in a separate video, I'll play with that a little bit more. The slicing thing was something that we could use with NumPy. Also, usually we use with normal lists. Um, we'll talk about NumPy in the next video more.